Welcome to this explainer. Today we are diving into the absolute universe of trigonometry. And hey, let's just toss out the idea that trig is some random, frustrating set of rules you just have to memorize, right? At its core, it's a brilliantly accessible, highly logical system that is built on the simplest of concepts, ratios. We are going to decode that entire system together. Okay, let's take a look at our roadmap for today. We'll be hitting 1. The power of right triangles. 2. Special triangles and angles. 3. The unit circle and radians. 4. Trigonometric identities and rules. 5. Solving any oblique triangle. And 6. Functions and beyond plane geometry. So before we get into the pure math, let's just look at a real-world scenario. How do you measure a towering 69.3-meter flagpost if you don't have a giant ladder and a huge measuring tape? Well, this is exactly what architects, engineers, and even game developers solve on a daily basis. By stepping back a known distance, say 40 meters, and measuring the ground angle to the top of the post, we can use trigonometry to instantly calculate that height. It literally replaces hard physical labor with smart logic.
All right, Section 1, the power of right triangles.
Every right triangle has 3 sides, and their names actually change depending on where you're looking from. Think of a classic paper cutter. You've got a horizontal guide, that is our adjacent side, right next to our angle of focus. Then you bring down the cutting blade, a perpendicular line, that's the opposite side, directly across from the angle. And the longest side, the one connecting them, that's always the hypotenuse. Naming these sides relative to our reference angle is absolutely the vital first step.
And here is where we find our trusty cheat code, SOHCATA. It perfectly sets up our 3 primary ratios. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But it doesn't stop there, because for every primary ratio there is a direct reciprocal. Cosecant is the flip of sine, secant flips cosine, and cotangent flips tangent. These 6 ratios, they are really the main engines of trigonometry. I want to pause here for a second to emphasize a crucial concept. Trig functions are fundamentally properties of angles, not triangles. Whether your 30-degree angle is inside some microscopic triangle on a computer chip or a massive triangle stretching all the way from the Earth to the moon, the ratio of its sides remains perfectly, immutably constant. Moving right along to Section 2, special triangles and angles.
We've got 2 very special shapes here that show up everywhere. On the left, the 45-45-90 isosceles triangle, where the 2 legs are perfectly equal. If they are length 1, the hypotenuse is exactly the square root of 2. On the right, imagine a perfectly equilateral triangle where every side is 2. If you slice it right down the middle, you get a 30-60-90 triangle. That one simple slice unlocks the exact fractional dimensions for 30 and 60 degrees, with sides of 1, 2, and the square root of 3. Because of those special triangles, we get this beautiful table of standard angles. Instead of messy decimals, we get these exact, clean values. And honestly, the extremes make perfect intuitive sense. Just look at the sine of 0 degrees. Imagine a ladder resting completely flat on the ground. The height of the wall it reaches, the opposite side, is 0. Therefore, the sine of 0 is simply 0. The math perfectly reflects the physical reality.
Section 3, the unit circle and radians.
Right triangles can only hold angles up to 90 degrees. So to map the rest of reality, we need a new way to measure angles, the radian. Imagine taking the radius of a circle, just picking it up, and bending it so it wraps perfectly along the outside edge. That exact angle it creates, that is 1 radian. And because the circumference of a circle is 2 times pi times the radius, it naturally takes exactly 2 pi radians to complete a full circle. Now, you might be wondering, why even bother with radians when we have degrees? Well, degrees are basically just a human invention. We just decided, for whatever reason, to chop a circle into 360 arbitrary slices. Radians, on the other hand, are abstract real numbers perfectly tied to these circles' inherent geometry. This is exactly why mathematicians, scientists, and engineers rely so heavily on radians the second they step into advanced calculus or physics. By combining those radians with an XY grid, we get the unit circle. It's simply a circle with a radius of exactly 1. And by locking the hypotenuse of our imaginary triangle at a length of 1, the math becomes almost ridiculously simple. The cosine of our angle is just the x-coordinate on the graph, and the sine is just the y-coordinate. You can literally just read the trig ratios right off the grid. And the cast rule perfectly illustrates this. Because our coordinates shift between positive and negative across the 4 quadrants of the graph, our trig ratios do too. We use the mnemonic all students take calculus to instantly know which ratios stay positive. In quadrant 1, all are positive. In 2, just sine. In 3, tangent. And in quadrant 4, cosine. It's just a perfect memory anchor.
Okay, on to section 4, trigonometric identities and rules.
These identities are kind of like the fundamental laws of physics, but for math. Remember the Pythagorean theorem, a squared plus b squared equals c squared? Well, on our unit circle, the sides are sine and cosine, and the hypotenuse is 1. That mathematically locks sine and cosine together forever in the rule sine squared plus cosine squared equals 1. We also have the quotient identity, proving that tangent is simply sine divided by cosine. And these foundational locks allow us to build even more complex tools, like sum and difference formulas to combine different angles, or double and half angle formulas to cleanly scale them up or down.
Section 5, solving any oblique triangle. So what happens when we break that 90-degree limitation entirely? When a triangle doesn't have a 90-degree corner, it's called an oblique triangle. Suddenly, SO katoa doesn't apply directly. So how do we calculate missing sides and angles for totally irregular shapes, like a weirdly shaped plot of land, or the flight path of an airplane battling crosswinds?
Well, we use a really simple 1, 2, 3 procedure, utilizing 2 brilliant extensions of our basic rules. First, identify what you know. Second, if you have matching pairs of opposing sides and angles, you use the law of sines, which proves their ratios are all equal. Third, if you have an angle trapped right between 2 known sides, you deploy the law of cosines, which is basically a heavy-duty, upgraded Pythagorean theorem for irregular triangles. You can even use those known sides and trapped angles to instantly calculate the exact area of the triangle without ever needing to know its true height.
Finally, section 6, functions and beyond plane geometry.
When we treat sine and cosine as functions, we have to look at their domain and range. The domain is the inputs, and they will happily accept literally any real number, any angle you throw at them. But the range, the output, or what we call the amplitude of the wave, is strictly bound between -1 and +1. And why is that? Because on our unit circle, a radius of 1 means the x and y coordinates can never physically stretch beyond those limits. Because we are constantly traveling around a circle, once we hit 2 pi radians, or 360 degrees, we're right back exactly where we started. This makes trigonometric functions periodic. If you graph them out, that continuous loop around the circle translates into infinite, perfectly repeating waves. And this is exactly how we mathematically model real-world phenomena like sound waves, light waves, and alternating electrical currents. And you know, trigonometry doesn't just stop on a flat piece of paper. When our canvas curves, the math adapts. In standard plane trigonometry, triangle angles add to exactly 180 degrees. But on a globe in spherical trigonometry, the angles actually exceed 180 degrees. And this is exactly how ships and satellites handle global navigation. In hyperbolic trigonometry, where space curves inward like a saddle, angles sum to less than 180 degrees, which is a concept that is absolutely vital to advanced theoretical physics.
It's honestly staggering when you take a step back and think about it. We started out by simply dividing the sides of a standard right-angled triangle, and step by step, those basic fractions expanded to map circles, plot out complex sound waves, and even navigate the sheer curvature of the globe. It leaves us with a pretty thrilling question. If simple right-angled ratios can expand to map the curvature of the universe itself, what other hidden dimensions of reality can mathematics uncover for us? Thank you so much for exploring trigonometry with me in this explainer. Keep wondering and definitely keep learning.